First off, we have Robert Huang from Caltech, who's going to tell us about random unitaries in extremely low depth.
Yeah, thank you so much for the invitation. Very happy to be here. So today I'll be talking about a joint work with Tommy Schuster and Jonas Haferkamp on random unitaries in extremely low depth. But personally for me, I think this talk is mostly going to be about understanding what cannot be learned in the quantum universe. So recently there have been a lot of progress in designing good algorithm for learning in the quantum universe with the goal of accelerating quantum science. However, there's also various aspects of our world that people try really hard, but cannot find an efficient algorithm to learn them. And hence it raises the following question. Are some basic aspects of our universe fundamentally hard to learn? And so interestingly, random unitaries, or more broadly speaking, one could say it's hard to learn or hard to measure, hard to observe, hard to see, hard to feel. And interestingly, random unitaries provide a very powerful tool, as I will talk about in today's talk, to understand and establish hardness of learning various fundamental aspects of our world. So random unitaries are not just powerful in this. I believe that from the morning session, they've also covered several importance of random unitaries. They're also very central in quantum information technology, from demonstrating quantum supremacy via random circuit sampling to benchmarking and learning quantum many-body devices, such as through classical shadow formalism. Random unitaries also provide a very powerful toy model for understanding complex quantum dynamics, such as the emergence of barren plateau and quantum neural networks, to studying quantum chaos and quantum gravity. For example, the famous fast scrambling conjecture asserts that black holes are the fastest scramblers in nature. And here, the prototypical dynamics for doing scrambling is a random unitary. And one of the most fundamental questions in the intersection of random unitaries and hardness of learning is the following question. But before diving into that, I will have to first talk about, I would just briefly mention the truly random unitary, which I believe have already been talked about. So a truly random unitary, also known as hard random unitary, is the uniform distribution over the entire unitary group. It requires exponential time to generate. So in the circuit model, it would be these exponentially deep quantum circuit that can create extraordinarily high entanglement. And when being applied onto any simple states, will generate exponentially high complexity. And one of the most basic questions between random unitary and hardness of learning is the following. Suppose that we have an unknown unitary that is either an exponential depth hard random unitary versus some extremely low depth random quantum circuit. Can we efficiently learn to tell apart these two? That is, can we efficiently learn to tell apart between these very short time dynamics from an exponential time hard random unitary? So that is going to be the main question that we will study in this talk. But to be more precise, we have to first characterize what we mean. So here, I would consider we to mean the most powerful model, which is we have a quantum agent. Think of it as, it could be an experimentalist with a full suite of quantum technology. So the experimentalist can generate arbitrary input state, possibly entangled with a quantum memory that it can accurately control. It feeds that input state into the unknown unitary. It can retrieve the output state using quantum sensor, store it in its quantum memory, and then process it using quantum computation to select the next input. And it can just keep doing this process for multiple rounds. And at the end, it needs to answer the question, is this unknown unitary a short time dynamics, or is it an exponentially complex hard random unitary? So in the talk in the morning session, there are two concepts for characterizing it. If the quantum agent cannot distinguish some short time dynamics from an exponential time hard random unitary under any K query, so it can have unbounded computational power, but it can only access the unknown unitary for K times, then it's known as K design. On the other hand, if the quantum agent can access U for an unbounded number of times, but it has to provide an answer within a polynomial time. That is, after polynomial time, it has to say whether it's a short time dynamics or an exponential time Hall random unitary. If it cannot tell apart, then we call that short time dynamics a pseudorandom unitary. So this question can also be formalized as the following. We're essentially asking, can unitary k-design and pseudorandom unitary be formed in extremely short amount of time? And how short can we actually generate them? So for example, in the morning session, generating both k-design and PRU, prior to this work, the best known construction would require a time that grows linearly in system size, which intuitively makes sense because people often think of k-design and PRU as a strong form of scrambling. And if you wanted to scramble an entire system, we have to at least like touch everything. So for example, in generating k-design, the result that Jonas talked about would be n times k. And for generating PRU, the PFC construction would actually require polynomial amount of time. But now we would like to ask, is it possible that we can do it much more efficiently? So in the following talk, I would first state the theorems that we proved in this work, and then I would talk about the proof ideas and the proof sketch for establishing the theorems, and finally talk about various applications, which a lot of the application will be focused on proving hardness of learning various basic physical quantities. So let me begin with the theorem statements. So the first theorem we proved states the following. It says, essentially just says, random unitary design, there's a way to generate them in logarithmic time on any geometry, including a 1D line. So for example, we can just set up a quantum circuit that looks like this, and it's a 1D geometry with nearest neighbor interactions. And now in logarithmic time, one could generate a very good random unitary design. And more precisely, if we wanted to generate random unitary k-design with an relative error, which is the strongest measure of error, epsilon, over n qubits, then it can be generated in k times log n over epsilon time. Or in the circuit model, k times log n over epsilon depth. So note that, especially the system size dependence improves exponentially over the previously best known result. And furthermore, the dependence on the k is also optimal. It's linear in k. So that's the first theorem. And similarly, there's a second theorem that we showed, which are closely related to the first one, which says that not only can we generate unitary designs very efficiently in just logarithmic time, we can also generate pseudorandom unitaries in polylogarithmic time, again on any geometry, including a 1D line shown here. It could also be in 2D, 3D, or some other expander graph, etc. In particular for here, if we restrict ourselves to all 12 connected circuits, then we can generate pseudorandom unitaries in just log n time. So an additional exponential improvement over this result. So note that these random unitaries that we're generating, they're very shallow. And because of the shallowness, they have very low complexity. And furthermore, because they're geometrically local circuits, they can only generate geometrically local entanglement. So one just really think about it as like a 1D shallow circuit, and every qubit is only going to be entangled with nearby neighbor. And because in polylog n time, it would only be able to entangle with polylog n neighbors on the 1D line. And however, despite all of these constraints, they are indistinguishable for any computationally bounded observer from an exponentially complex Hall random unitary. So an immediate consequence of this theorem is the following. Basically, this provides this immediately says that if we now use these pseudorandom unitaries, very shallow ones, apply it onto any state. So it could be some product state, it could be some quantum state with some entanglement structure. If we just apply it into any state, it will essentially turn it into being indistinguishable from Hall random state. And that's just the property of Hall random unitary. Applying Hall random unitary to any state would generate Hall random state. And since pseudorandom unitaries, these very shallow circuit, they're indistinguishable from hard-random unitary. So if we now apply these shallow circuits onto any state, it would turn it into a state that is indistinguishable from hard-random exponentially complex states, but it only adds a tiny bit of complexity. And furthermore, because these circuits are shallow, we would not really change the long-range entanglement. It would not change the entanglement structure of the state that we apply to. So for example, if the state that we apply to has long-range entanglement, then after that, it would still have long-range entanglement. And if the state doesn't have long-range entanglement, the output state would still not have long-range entanglement. These shallow circuits are really just entangling things and perturbing things very locally. Okay, so these two theorems, we can now, with these two theorems, we can go back to this question. And that, can we learn to efficiently tell apart between very short time dynamics from exponential time hard-random unitaries? And because of the existence of these shallow PRUs or these very low depth unitary design, the answer is immediately no. We cannot. There's no way for any polynomial time quantum algorithm, including future experimentalists, to tell apart short time physical dynamics from exponential time hard-random unitary. Oh, sorry, if they're.
If I give you a controlled unitary, I mean, would the same statement work? Or?
Yeah, even with controlled. That's a so there's one thing that I do know. If you are given time reversal, like you can evolve forward in time and also backward in time, then these statements would not be true. These statements are only true when we only access forward time evolution, but not the ability to control forward and backward. In terms of if it's a controlled evolution, that's a good question too. I think we're not entirely sure what the answer to that is at the moment.
PRU is like almost certainly true.
PRU is true, but it's the low depth one. So for if the goal is to, if you're asking, does PRU still like, suppose now I have this polynomial sized quantum circuit and I wanted to say that this is indistinguishable from hard even with control and control inverse, that's true. But the thing that's not very certain, which I do believe that it should still be true, is this very low depth one. Okay, so now after talking about the results, let's try to compare this to the classical world. So for classical dynamics, one can also ask the same question. How fast could a random, say, classical reversible dynamics become indistinguishable from a truly random one? So does there also exist these like very shallow or very fast scrambling behavior? And the short answer is no. And hopefully the pictures shown there already illustrate it. But essentially the idea is this. If we put in two bit strings, one is all 0, and the second one is everything is 0, but the first one is 1, then one can see that because when it's shallow, then this change in the first bit would only affect a small subsystem. And all the rest of the system will remain unchanged. On the other hand, if we have a truly random classical dynamics, like an exponential time one, then when we flip the first bit, then the whole output bit string should just change. And hence, when we see that it only changes, say, for example, the first half of a system, then we immediately know that this is a shallow classical dynamics, and it's distinguishable from a truly random one. And hence, just using this argument, one can immediately prove that in order to generate classical dynamics that look truly random, it will require linear time. Sorry? Yeah, so behave random, one could say, like, note that there are a few definitions, like designs or PRU. Here, behave random can be either of that. So if one wants to have a random classical circuit that's shallow, or a random classical circuit to form just two design, then one can prove that it requires linear time. Similarly, for being pseudorandom. If we want the classical circuit to be pseudorandom, it would also require linear time to generate. On the other hand, for quantum dynamics, we see that it only needs logarithmic time or polylogarithmic time to behave random, to form unitary design or to form pseudorandom unitary. And what happens essentially here is that one could do the same kind of experiments, like put in all 0 or put in the first 1 on the first side and 0 everything else. If one do this experiment, what essentially happens is there still be a light cone thing, like the output state, for the input B will differ from the output state for input A by only applying a operator on subsystem. However, there's no way to efficiently check that because we don't really know what's the right basis to measure in. So in classical dynamics, we know that there's just one basis. There's a standard computational basis. We just measure it there, and now we will see the difference. But here for quantum dynamics, what essentially happens is that because we don't know what is the right basis to measure things in due to non-commutativity, and that essentially hinders it and causes even just a log depth 1D circuit to form pseudorandom unitary and to form unitary designs. However, I show also that this is not quite, this is not just about quantum versus classical. In a way, it's more about unitary. So unitary are kind of special in having this property. If we now restrict ourselves to, again, quantum dynamics, but dynamics that satisfy time reversal symmetry, then one can also prove that one needs linear time to behave random. So for dynamics that satisfy time reversal symmetry, it's essentially just an orthogonal, orthogonal matrix. And for orthogonal matrices or orthogonal evolutions, what basically happens is one can essentially design similar experiments, but involving Bell pairs, and use the fact that when you have a Bell pair, if you apply the forward evolution on one side, it essentially becomes an inverse evolution on the other side, and could use that to do testing. So in a way, this is a phenomenon about quantum unitary dynamics. And quantum orthogonal dynamics actually will also require linear time instead of logarithmic time. So now, after talking about the theorems, I would like to dive into the proof of these results. And the key tool that we use to establish the result is known as the gluing lemma, which Fermi has briefly mentioned in his talk. But here I would like to dive into it more deeply and showcase how gluing lemma allows us to prove theorem 1 and 2 on the generation of these random unitaries in extremely low depths. So the gluing lemma essentially sets the following. Suppose we now consider a very big system, arbitrary big, and this pink unitary acts on everything to the left, and the orange unitary acts on everything to the right. However, the two overlaps on a small number of qubits. And suppose that each of them, there are random unitaries that are indistinguishable from hard. So here, indistinguishable from hard can mean it's a unitary design or it's a pseudorandom unitary. Gluing lemma applies to both cases. And basically, if we have these two blocks that are indistinguishable from hard, or we can just think of them as hard random unitaries, both of them, then now when we overlap by order log k over epsilon qubits, just a small number of qubits, then we can show that the composition, the composed unitary, under k queries will be at most epsilon distinguishable from hard. So here it means that if we have a quantum algorithm that can access this composition for k times, it can run whatever computation it wants, quantum computation, then the output state will be at most epsilon far away in trace distance from the one that was obtained by applying a true hard random unitary. So this is the kind of the main crux of the argument. So another way to say this is together by combining them this way, by overlapping on log k over epsilon qubits, it will form epsilon approximate unitary k design. And note that the dependence on k and epsilon are both logarithmic, meaning that it can easily form, say, like superpolynomial design if we just put in slightly above logarithmic number of qubits. So now what I would like to do is to provide a proof sketch of this gluing lemma. So note that there are, even until now, we know of several ways of proving the gluing lemma. One way is to utilize this path recording oracle that Fermi talked about. One can prove that in a more elementary fashion. But if one is familiar with Weingarten calculus and approximate orthogonality of permutations, then there's also a short proof that uses these more advanced techniques. So here I'm just going to talk about how that short proof looks like if we assume knowledge of Weingarten calculus. So first, we will divide up the system into A, B, and C. The B is just the overlap, and A is the one that the pink unitary acts on, and the C is the one that the orange one acts on. Then now one can use the following result. So if we now look at essentially K queries to these two objects. So K queries to this pink one, which would correspond to this K copy or K-wise Turing channel. Then using Weingarten calculus and approximate orthogonality, one can essentially prove that the K copy Turing channel can be written as this form succinctly, where this DAB corresponds to the dimension of system A and system B. So for people that are familiar with Weingarten calculus, this step might seem like I'm missing a bunch of terms, because usually in Weingarten calculus, there will also be these cross terms where instead of considering just a single permutation pi, we will have, say, pi and tau. And the thing inside the trace would be, say, tau inverse, and the thing outside is pi. And then there will be this Weingarten function, which is kind of crazy. But what one essentially can show from approximate orthogonality of permutations is that we can drop the off-diagonal terms and just keep this and incur a small relative error. And similarly, similar statement holds for the orange one as well. So there we can also just replace this orange unitary, say K copy of them, and now we average over them. Now the Turing channel would be of that form. And the last step is also just approximate orthogonality of permutation, which says, now note that in the system B part, there will be this permutation that's also acting on the qubits in system B. These permutation will be fed into the trace of pi inverse, like that, the empty space there. And now we just use the fact that if the two permutation it's not the same, then suddenly there's a very strong decay, because the system, even when the system B is only of logarithmic number of qubits, there will be a strong decay. And hence we can just throw out the contributions when pi and tau are not equal. And basically what one can show is together this, because tau now has to equal to pi in order to provide a good contribution. Together it just says that the composed Turing channel, the channel corresponding to the applying K copies of this composition would be looking like this form. And this is just the Turing channel, the approximate Turing channel for hard-random unitaries. And that essentially concludes the proof to say that this is an epsilon approximate unitary K design. The epsilon just come from every time I wrote this approximate sign, there's an epsilon error. And then the K design part just come from the fact that this is a K-fold Turing channel. So now the gluing lemma essentially says if we have indistinguishable or random unitary indistinguishable from R, a pink one, composed with the orange one, then together they will form epsilon approximate unitary K design. So now how do we go from this gluing two object into these statements about generating random unitary design and pseudorandom unitary in such a low depth? The idea is as follows. So we're just going to apply gluing lemma multiple rounds. First, we'll start by gluing these two blocks. So instead of considering them to act on arbitrary number of things, we're just going to consider this pink and orange one to be roughly twice the size of their overlap. So now together, when we put them together, it forms this like Z-shaped Tetris block. And then from the gluing lemma, we know this would be an epsilon approximate unitary K design. And now we apply gluing lemma again, but now we glue together this, this dashed line, this whole block. Think of that as, because it's also indistinguishable from har under K queries, and this blue one. So applying gluing lemma again and using triangle inequality says together these 3 block shape would form a 2 epsilon approximate unitary K design. And now we can do the same, but now glue this dashed line block, which is now growing, with that light blue block. And that formed 3 epsilon approximate unitary K design. And then we can just keep using this strategy to grow it. So now adding this yellow one creates 4 epsilon approximate unitary K design. This green one creates 5 epsilon approximate unitary K design. And then we just keep doing it until it expands out to the entire n-qubit system. Then together, I'm overcounting a bit, but it will form an epsilon approximate unitary K design. So now what it essentially says is if we now have these small blocks that are just roughly of order log K over epsilon, and each of them overlaps some order log K over epsilon things, and we just place them in this 2-layer brickwork structure, then together, this whole thing will form an epsilon approximate unitary K design over n qubits. And this logarithmic on both K and epsilon is very crucial here, because now what we can do is we can take epsilon to be smaller than any polynomial function or inverse polynomial function, and take K to be bigger than any polynomial function. So K equal to n to the little omega of 1. Now, by plugging this in, it essentially says together, this whole thing, this shallow circuit, this structure would already form an 1 over superpoly n approximate unitary superpoly n design, which is just indistinguishable from har, since, yeah, for any polynomial time algorithm, one is not gonna query that much. And now we can also plug in this epsilon and K scaling into this thing here. And due to the log that applies to both K and epsilon, we just need the overlaps to be slightly above log n. So now, from gluing these 2 blocks, we immediately get the following. Suppose we have this structure that looks like this. Each of the blocks only acts on slightly more than log n qubits, and each of them itself is indistinguishable from har. Then together, when we place them together like this, this whole circuit will be indistinguishable from an n-qubit har random unitary. So note that previously, this is just indistinguishable from the local har that acts on a small number of qubits. But now by just placing them this way, it will be indistinguishable from a har random unitary that acts on the entire n-qubit system. So more formally, the gluing lemma, or the more advanced version of the gluing lemma, not just gluing 2 of them, but gluing a bunch, states the following. If we now compose a bunch of small har random unitaries, each of them, say, is over log nk over epsilon qubits in this figure A fashion, then together it will form an epsilon approximate unitary K design over n qubits. And from here, it's pretty straightforward to derive both theorem 1 and theorem 2. To get theorem 1, we just replace these small har random unitaries by the best known K design. For example, the construction that Jonas has talked about, which is just a standard 2-qubit brickwork circuit. If we just replace that, then we immediately get theorem 1, which says random unitary K design can be generated in K log n time instead of the original K times n. So one way to think about this gluing lemma, it's essentially a compilation technique that allows us to always compress down the depths. On the other hand, for getting theorem 2, we just replace these small har random unitaries by existing pseudorandom unitary. For example, this PFC construction that Fermi talked about. Then we get theorem 2, which says that pseudorandom unitaries can be generated in poly log n time. And the reason that it's poly log n is because this PFC construction requires polynomial depth. And since it's only a polynomial depth over slightly more than log n qubits, it would just be poly log n. And that concludes the proof for these theorems. And now finally, what I want to do is to talk about what are the interesting applications that can come out of this result. So the first example, which also contains a lot of different instances is in establishing hardness of learning. By utilizing the existence of these random unitaries, random shallow circuits that are indistinguishable from hard random unitaries, one can derive that a large number of very natural learning problems are actually hard, even though they seem kind of easy. So the most immediate one that just immediately come from the result is answering the question of whether we can feel time. So suppose that there is an unknown unitary u that is either a 1D short time dynamics or say a 1D but exponential time dynamics. Then one can ask, can we feel the difference between their time? Because one is very short time, like say polylog time, but one is exponential time. So they differ by doubly exponential amount of time. Can we feel this vast difference in their kind of time, like the time evolved inside? And it's not hard to see that using the construction of these PRU, one can just suppose that we can indeed distinguish between the two, then one would be able to distinguish between these shallow PRU versus true hard random unitary, which is a contradiction to theorem 2. And hence the answer to this is no, because these low depth PRU exist, so time is not really feelable. We can feel the difference between a constant time dynamics and an exponential ones or a higher one, but whenever it's short, means like polylog, then suddenly there's no hope to distinguish them. And similarly, not only time is not physically observable, causal structures are also not physically observable. So here one can consider the following setting. Suppose we have an unknown unitary that is generated by quantum dynamics consisting only of short-range interactions or long-range interactions. So the short-range one, say it's on 2D and everything just, every qubit just talks to the nearest neighbor. The long-range one is, different spins can interact with things very far apart. Then in a short time, if we evolve under these dynamics for a short time, they will generate very different causal structure. The short-range one would have a causal cone that only includes things that are nearby. But the long-range one would have a causal cone that includes things that are very far away. But essentially, it's not hard to use the technique that we talked about to show that both of them can already look like hard random unitary, and hence they would look the same. So there's no way to efficiently tell apart different causal structure or light cone structure. On the other hand, it's also not hard to show that if we now consider a more powerful observer that can reverse time, similar to what we just talked about, then essentially what that more powerful agent could do is they can implement like a butterfly experiments to calculate OTOC. So from calculating OTOC, from the OTOC values, this more powerful observer that can reverse time can distinguish the two easily. So essentially just go back in time, inject the butterfly and come back, and now it sees how far it has spread in order to figure out if it's short range or long range interacting systems, and to figure out the causal structure, the light cone structure. But for a standard quantum agent that can only access forward time evolution, which in many physical experiments, it doesn't seem conceivable to have reverse time evolution, then it would not be able to tell them apart. Another important physical concept that is also hard to observe is topological order. Basically, it's well known, like the definition of topological order is that essentially the characterization of long-range entanglement, and it's known to be preserved under perturbation by shallow geometrically local circuits. So for example, the torical ground state will require square root n depths to generate in 2D, and hence any little o square root n depths 2D circuit will preserve topological order. In particular, polylog depth circuit would also preserve their long-range entanglement. And an open question in the intersection of learning and quantum is that given copies of a state psi that either come from this family or that one, which is it's either the torical ground state perturbed by a shallow 2D circuit, or a product state perturbed by shallow 2D circuit, can we efficiently classify if it's in this class or not, if it's in the topological family or the trivial family? And again, immediately from the existence of shallow PRU, the answer is no, because shallow 2D circuits, they can hide topological order. Note that they don't change topological order, they just hide it. Because essentially what happens is these shallow 2D circuit, they're indistinguishable hard-random unitary. And we also know that hard-random unitaries apply onto any state would generate hard-random state. And hence, if we have a random state that come from either the topological family or the trivial family, then these random states, they would both look like hard-random state, and hence it's not possible to distinguish them. So those are just a few examples where one can establish hardness of learning. But there are also various other implications that can come out of these shallow random unitary circuits, which I believe Adam Boland and people here, as well as Umesh Razurani and Li Chen, has some interesting implications that says if we are a boundary observer and can only act and observe and do experiments on the boundary state, then it will be hard to figure out the geometry inside. And to establish that result, one can also use this shallow random unitary construction.
Like morally, like every single application, like it just falls in the bucket of like any task, any like property that is like not completely scrambled by a shallow circuit. Like literally anything that is not scrambled by a shallow circuit is going to be hard to learn, right?
That's right. That's right. That's right. So really, like a lot of things are going to be hard to learn.
Well, I can hold this question until the end of the talk, but I see the symmetry broken word there. I see. Let me ask there.
Ah.
So we know this proof breaks down if we impose reality. And physical analog of that would be the time reversal symmetry.
Yes.
So a small amount of symmetry now disallows these super shallow designs.
So for time reversal symmetry, yes, but for other symmetry, we don't know yet. I don't know.
Okay.
So indeed, I think if one considers, say, some SPT phases that has a time that considers time reversal symmetry, then it's not clear that they're going to be hard to learn. They could be very easy to learn because at least we know these shallow random unitary result only holds when we focus on unitaries, but not unitaries that have time reversal symmetry. However, there's also tons of other symmetry, and I don't know the answer to the other symmetries.
So one more continuing question then. So the place where this symmetry plays a role is probably in the approximate orthogonality in the complements of in the commutant of the tensor representation.
That's right. Yes.
So, but the small amount of like time reversal that somehow blows up that commutant a little bit, and that's just totally breaks all the argument. Is that fair understanding?
Yes. So it's like for orthogonal, yeah. If we go to very early here, the permutation picture only applies to unitary, right? So like if we have time reversal symmetric dynamics, then there will be like also these bell pairs that emerges. And bell pairs, they don't have these they don't have these nice approximate orthogonality, and hence when we consider time reversal symmetric unitaries, then suddenly even like this step already is wrong. This step definitely wrong, and I mean the whole proof just breaks down. That's right. But yeah, but understanding what kind of symmetric quantum dynamics would be subject to these this type of like shallow, like very fast scrambling, I would say is still unknown. Time reversal symmetry is one that's known. Okay, so not only can it be very useful for proving hardness of learning, in a sense, proving negative results about what we can learn in this world, it can also be useful for establishing advantage in learning. And the kind of the high level idea is that sometimes there will be these hardness of learning result, but it only applies to classical agent, but not to quantum agent. And in those cases, one can establish advantages of quantum agents over classical in learning various physical systems. So just kind of a brief recap. So a classical agent is an agent that can conduct many experiments of the following form. It can prepare a state, evolve under some unknown quantum dynamics, E, think of it as a channel, and then perform some measurement to obtain classical data. It can then take that classical data, store it in its classical memory, process it using classical computation to select the next experiment. So in a way, one can think of classical agent as being able to access physical system in a very classical way using measurements. On the other hand, the quantum agent that we have been talking about, it can conduct experiments in a quantum way because it can utilize quantum sensor, quantum memory, and quantum computation. So it can feed in some quantum state that's entangled with itself, and then retrieve the quantum state and process it using quantum computation. And one can ask, like, what kind of advantages can we get if we use quantum agent to learn about the physical world versus using classical agents? And previously, there's a well-known result, which is the following. It says, suppose the unknown physical dynamics are two extremes. One is just a complete depolarizing channel that maps every possible state to a maximic state, or it's a generic unitary sample from the hard measure, so a hard random unitary. Then in our previous work, along with Jordan Kotler, Sitan Chen, Jerry Lee, and others, we proved that classical agents would require an exponential amount of time to distinguish between these two cases. On the other hand, a quantum agent only requires a constant amount of time to distinguish between these two cases. However, there's a problem here, which is a generic unitary U is non-physical. It's too complicated. So one could ask, what does this result still hold if we consider a 1D generic short time dynamics, so just some 1D shallow circuit? And now using this result that says 1D shallow circuits are indistinguishable from hard random unitary, we can immediately obtain the following theorem, which says if the goal is now to distinguish between two physically meaningful setting, one is a complete depolarizing channel, a super noisy channel, versus a pure unitary dynamics, then classical agents would require superpolynomial time to distinguish them, but a quantum agent only requires constant amount of time to distinguish them. Just immediately following from the previous theorems and the fact that 1D short time dynamics can be indistinguishable from hard random unitary. Oh.
Good question. One thing that you had, with this work was you had a really nice experimental demonstration on it as well.
Right.
If you could describe like what the hidden constants in your big O notation are, are they good enough that you could actually implement a really shallow depth circuit thing as a T-design experimentally?
Yeah, that's a great question. Yes, so actually in the paper, if you look closely in the appendix, we spell out the exact number, like there's like a 4 and 5 somewhere like that. But it's pretty, and also it's like a big equation. But yes, but we've done some, like, yeah, it's a, like, even though here I presented the big O notation, but the constant in front is pretty small and it can also be calculated. So yes, no problem. Yeah, so that's the second example. Here's a third one, which is kind of a very different flavor than the first two, which is the existence of these shallow random unitaries can also lead to faster learning. It not only hinders learning various important properties, it somehow, if we use it in a different way, it can also lead to faster learning protocols. And the idea is that there have been a lot of different learning protocols that are based on quantum scrambling or quantum chaos. Then in general, they can be just significantly improved because now it says that these random unitaries or these scrambling unitaries, they can be generated in a very short amount of time, and hence it can lead to more efficient learning. So here's one example based on classical shallow formalism. So in classical shadow formalism, if we wanted to estimate some highly non-local properties, such as many-body overlap or fidelity with some target state, the target state is highly entangled, then in order to do the learning, do the estimation, it will require running a protocol like this, where we have our unknown state, and then we just scramble it using a deep Clifford circuit, and finally ends with some single qubit measurements. And it's well known that even until now, running deep Clifford circuit is still experimentally very challenging. And hence, an open question in the literature about learning quantum systems is, if we now replace these deep Clifford circuit by, say, a one-dimensional or two-dimensional log depth Clifford circuit, can these shallow circuits be as powerful as deep circuits in learning? So previously, there have been numerical studies on this, where it shows that it seems like for learning certain states, a shallow circuit seems quite powerful, and then there's also some physical argument by Bedica and Mateo and others that shows that it seems like this should be possible, but more formally, this still remains an open question. But now using theorem 1, essentially one can very easily show that a 1D log depth Clifford circuit would form a very good unitary 3 design. And note that in classical shallow formalism, all we need is 3 designs, and hence shallow circuits are as powerful as deep circuits in learning highly non-local properties. So now one can just always use a shallow random circuit instead of a deep one. So now to conclude, in this work, we proved that both random unitary designs and pseudorandom unitaries can be generated in extremely low depths on any geometry, including 1D line, 2D, etc. And as a result, many fundamental physical quantities can be shown to be provably hard to learn, feel, or see them, such as time, causality, topological order, etc. And furthermore, I just wanted to post this, is that if we, like in various prior work, people have often considered scrambling to be defined in the formation of unitary designs or PRUs. Then in light of this result, it essentially says, if that's how we define scrambling, then even a 1D quantum systems would have a scrambling time near logarithmic in n. And in an all-to-all connected quantum system, the scrambling time would be log n, which is exponentially faster than this conjecture. So something must be wrong, and we should try to address that in the future. So thank you so much for listening.
Just to make sure something very basic about your first point. So except causality, do we really need shallowness to make the statement that time and topological order are not feelable? Wouldn't just ordinary PRU, like what Fermi talk about this morning, be enough?
So for topological order, no, like, because here if you just implement like a polynomial sized quantum circuit, it would just like, yeah, the long range entanglement could be destroyed. So only when you consider shallow circuit, the long range entanglement will be preserved. And hence for this, one needs these shallow construction. But time is a good point. Actually, even what the work that Fermi and I did also showcases this. But in that case, it would be a 1D polynomial time dynamics versus 1D exponential time dynamics, and then we cannot feel the difference. But now this essentially strengthens it to be 1D polylog time dynamics versus 1D exponential time dynamics. So it says even in these two extremes, we can still not feel the difference.
Regarding your comment in the last page, so if I compare, say, the fast scrambler case with your log n depth circuit, they are certainly using different criteria, right? So if I think about, say, operator size growth, then in the model like with maximal chaos, then the operator size grows exponentially, and it will grow from size order 1 to size order n in time log n. And in the circuit you have, this will not happen, right? Because you have depth log n, your size will only go to log n.
Right.
So that shows that somehow the scrambling criteria like operator size are not a problem with your design statements.
Yeah,
like they're not observable.
I think that's not enough. Right? Like one would not say if I have a circuit that will turn single qubit operator into n-qubit ones, then it's scrambling. It's not right.
So why then it's I still don't have the intuition why in that case it's so hard to distinguish the circuit
yeah,
with
the reason,
randomness.
the reason is because the following. It's like you cannot really see operator growth. Like if I am an experimentalist that I can only access forward time evolution, our result is essentially saying that you cannot access operator growth. You can have two parallel copies.
As it's just observable. I can just have
this have to be U dagger. Like essentially you need time reversal. That's
Okay.
related to this causal structure thing that I was talking about earlier, which is like if you are this more powerful observer that can reverse time, then yes, then operator growth will be visible to you, and causal structure will be visible and so on. But if I'm just an ordinary experimentalist that can only access forward in time, not reversing time, then suddenly operator growth is no longer a visible thing.
I'm a bit confused about your comment with symmetry. So if I have no time reversal symmetry, but I have another symmetry, and I like some Z2 symmetry, and I start from a broken symmetry state, then with a shallow circuit, I should still have like a finite magnetization. This has to be something macroscopic that I should be able to measure to some kind of good precision. So why is that lost after a shallow circuit?
Oh, you mean like
Yeah,
So note that
pseudo magnetization. Although it's not time.
Say magnetization, often let's say just sum of Z. But then after we perturb it by some unknown shallow circuit, then suddenly we don't know what's the Z's can become random directions that we don't know of. And
yeah.
But I should also say we don't have any results about symmetry broken yet. So it could be that distinguishing between say symmetry broken phase versus topological or some other things can still be easy. In particular, like if the symmetry is like time reversal symmetry, then it seems like all these results would not hold.
Yeah.
Here is solely about this notion of gap quantum phases, which can consider arbitrary quantum circuit. Then it's in that case, which is the more prototypical trivial versus topological, and that's hard to distinguish. But trivial versus symmetry broken, maybe that could still be easy.
If we don't have more questions, let's thank the speaker again. The next talk will be given by Matteo Ippoliti from UT Austin. He'll be telling us about, I think, deep thermalization and pseudo entanglement.